Swayam Prabha. Digital India. Educated India.
Hello everyone. Another question we can ask here is how the rate of decay is dependent on damping, right. So, the energy of the system, how it is dissipated, and how it is rated with the damping in the system. So, for that purpose let us try to look at decay of energy, decay of system energy. The energy of the system, it consists of two parts, the kinetic energy and potential energy, right. And therefore, at any instant of time we can find kinetic energy of this single degree of freedom system as half mx dot square plus half potential energy is half kx square, right. So, it means if I am given x of t and x dot of t, I can then determine E of t, right. So, if x of t and x dot of t are given, then we can determine how the energy of the system varies with time, right. And now if you make a plot of this as a function of time, then we would understand that how the system energy is decaying with time. So, let us try to sketch these plots, when we have, let us say, first overdamped systems, right. So, if you take overdamped systems, then if you plot the E is a function of time. By the way, why E is supposed to change with time, why it is going to decrease with time? Simply because there is damping in the system. The system would decay, would dissipate this energy as the vibration proceeds, right, as it progresses, right. So, in every dt time the system, some of the energy would be lost in doing work against damping forces, right, and therefore, system energy is going to decay with time. So, let us talk of underdamped system. So, if we take a system which is underdamped, then and if we assume the damping factor, let us assume that the mass and stiffness are same for all these systems, and if the damping factor is very high, and the limit could be, say, infinitely large value of damping factor. So, in that case the system energy would not decay with time, because the infinite damping force would not allow system to displace or deform, and hence there would be no loss of energy, right. Though damping force is high, but there is no deformation or velocity, and hence there is no loss of energy, and hence what is going to happen? We will simply have the energy of the system staying constant. So, this is when damping factor is theoretically infinite. Now, when damping factor is reduced, then the rate of the energy would start decaying, right. So, if you increase the damping factor, then system energy would start decaying in this manner as with time, and then if you reduce the damping factor further, again the rate of decay would increase, increase like this, and then it would reach to a maximum decay value, right. This is when the damping factor is equal to 1, right. When the system is critically damped, the rate of decay of energy would be maximum for an overdamped system, right. So, this is nothing but the zeta reducing, zeta is reducing in this direction, right. Now, let us talk of underdamped systems. Now, for the underdamped systems, we can have the smallest damping possible as no damping, right, when damping is 0. So, in that case again the system energy is not going to decay with time, the total energy of the system would stay constant, and hence we will have energy of the system staying constant with time. So, such a system would keep on vibrating and the total energy of the system would stay constant. Only the kinetic and potential energies instantaneously will be changing and changing hands basically, right. Kinetic energy converting to potential energy and potential energy converting back to kinetic energy, but the total energy would stay constant. But now if we have some damping, right, then what is going to happen is that the system energy would then start decaying, total energy will start reducing with time, and then the graph may look something like this, okay. So, that is when now there is some zeta, and if you increase the damping further but keeping the system under damped, then the rate of energy decay would increase more, right, it would further increase like this, and then when it becomes almost close to 1, right, little bit less than 1, because if it becomes equal to 1, system no longer would be under damped, right. So, if you keep it almost close to 1, then it would basically reach to the rate of decay closer equal to that of a critically damped system. So, this would be the basically damping level in the system. So, this is when zeta is almost equal to 1 or but little bit less than 1, so that it remains under damped. So, what we see is that, so here if I show the damping level, so this is zeta is equal to 0, right, and this is zeta is equal to 1. So, you can see here damping is basically increasing. So, from this I think discussion some important points emerge. One thing is that we can't say that if damping is increased, then the decay of system energy or displacement is always going to increase, right, it is going to, the rate of decay is going to increase, right. There is no monotonous change, because we see that for overdamped systems the rate of decay increases when the zeta is reduced, but for underdamped systems rate of decay increases if zeta is increased, right. So, these are two opposite effects. So, the point is that the power dissipated from the system, or the rate of dissipation of energy, which is nothing but the power dissipated, it depends on the damping force and the velocity. So, having higher damping factor will increase the damping force, but the other quantity which affects power dissipation is velocity, and that also is affected because of damping factor, and therefore both need to be seen to determine the power dissipation, right. So, therefore system with with damping factor equal to the critical value, that will have the highest rate of decay of energy, right. So, the rate of decay of energy is highest when the system damping is equal to critical damping, right. So, the rate of decay is highest when system is critically damped. Okay. So this is the other important thing we need to look at is is there a relationship between the ratio of amplitudes, right, in different cycles with the damping factor, and that relationship is captured by what is called as logarithmic decrement. So now we talk about what is called as logarithmic decrement. Logarithmic decrement basically gives the relationship between the ratio of amplitudes of different cycles of vibration with the damping factor, right. So we know that the equation for free vibration of an underdamped system is given by a to the power minus zeta omega n t cos omega n under root of 1 minus zeta square t minus phi. And if we sketch the free vibration profile, then it may look something like this. And so on. So, if let us say the amplitude here at instant t1, which represents the time when the amplitude is reached, that is x1, and say after n number of cycles, right, if the amplitude is xn, then we would like to determine. So, at instant t1 we reach an amplitude xn after a lapse of n number of cycles, then what is the ratio of x1 and xn? That is what we would like to determine. So, therefore, we would like to write x1, and we will like to find x1 as x at t1, and that would be nothing but a e to the power minus zeta omega n t1 cos omega n under root of 1 minus zeta square t1 minus phi, right. Similarly, we can write down xn xtn is equal to a e to the power minus zeta omega n tn cos omega n under root of 1 minus zeta square tn minus 1, right. So, now we note that tn is nothing but t1 plus n times t, because n cycles are elapsed, right. So, therefore, the time tn would be t1 plus n times the time period. So, this is nothing but the time period t, right, time period of damped oscillations. So, if we now and another thing we note that the cos function is a periodic function, right. So, it means cos omega n under root of 1 minus zeta square t1 minus phi, it will repeat periodically, and hence cos, it will be equal to cos omega n under root of 1 minus zeta square t n minus phi. So, these two are basically equal, right, and therefore, if we take the ratio now x1 upon xn, what we get is a e to the power minus zeta omega n t1 upon a e to the power minus zeta omega n t n, and if you substitute t n here, what we get is e to the power, so a of course cancels out, and then we get e to the power zeta omega n, right, into n t, that is what we get, right. And we also note that the t, which is the time period, it is equal to 2 pi upon omega d, right, which is the damped natural frequency, and damped natural frequency is nothing but omega n under root of 1 minus zeta square. So, this is nothing but t. So, in the light of this, we can then write x1 by xn is equal to e to the power zeta zeta omega n into 2 pi upon omega n under root of 1 minus zeta square. So, omega n cancels out, and then we are left with x1 upon xn is equal to e to the power zeta, maybe let me rewrite again, e to the power 2 pi, right, zeta n upon under root of 1 minus zeta square, that is what we get, okay. and if you go to next page, now if you take log of the two sides, then we get log of x1 upon xn is equal to log of e to the power 2 pi zeta n, right, upon under root of 1 minus zeta square, which leads to 2 pi zeta upon under root of 1 minus zeta square is equal to 1 by n log of e x1 by xn. So, I think this is the final expression we are getting, right, which basically relates the amplitude at the beginning of at some amplitude at some cycle at the beginning of a cycle, and then amplitude after elapse of n cycles, right. So, that ratio, that is x1 by x1, and then n is the number of cycles which are elapsed. So, and this therefore quantity is dependent on only zeta, right, and this quantity then we refer as logarithmic decrement. So, we define this as 1 by n log of e x1 by xn. So, this is nothing but logarithmic decrement. And this quantity you can see it depends only on zeta. So, this particular relationship has a great practical value, because we can use this to determine damping in the system. So, if we have a system, let us say single degree of freedom system, and if we know the displacement versus time history under free vibration of that system, if we know the displacement versus time history like this, which can be obtained let us say by measurement, then we can use this relationship to find damping factor in the system. So, we can measure say x1, and then we can measure this x2, right. So, in the present case what is going to happen, x1 by x2, because here n is just 1, right, because only one cycle is elapsed, then in that case this would be simply log of e x1 x2 would be simply equal to 2 pi zeta upon under root of 1 minus zeta square. And then because x1 x2 can be obtained from the measurement, we can find zeta from here, right, we can find zeta in the system. So, damping in the system can be estimated in this manner. Let us now consider the force vibration of the single degree of freedom system with viscous damping, and we are basically going to consider the harmonic forces, right. So, force vibration right, and the equation of motion with force vibration can be written as mx double dot plus cx dot plus kx is equal to f of t, right, and here f of t is a harmonic force. So, f of t, let us say it is a cosine force f naught cos omega t, where omega is the excitation frequency. Now, the response of the system would consist of two parts, right, complementary part and particular part. So, the x of t will be equal to xct plus xpt, the complementary part and particular part. So, let us first of all find the particular part or particular solution. Let us determine this first. And now we are going to use here the complex exponential method we studied earlier in the force vibration analysis of undamped system. Okay. So, in the complex exponential method we basically find the response of the system to complex exponential force. Okay. And then once the response has been found, we then take the real part of the response. Okay. So, that is the method we studied earlier. So, let us take the complex exponential force as f of t is equal to f naught e to the power I omega t, and we can see that the real part of f bar t is basically the actual force f of t. Now, let the particular part of the solution to this complex exponential force is given by x p bar t, right, is equal to x p o bar e to the power I omega t. So, we are assuming the response to be of the same form, it is at the same frequency omega, and its amplitude is xpo bar. Okay. So, this xpo bar in general could be complex, and xp bar is the particular part of the response. So, the over bar has been used to indicate the complex exponential nature of that quantity. So, if you substitute this in the equation of motion, what do you get? Minus m omega square xpo bar plus I omega, right, c xpo bar plus k xpo bar, okay, and then e to the power I omega t would cancel out from the right and left hand side. So, this is what we get, and therefore, if you simplify, what we get is xpo bar is equal to f naught upon k minus m omega square plus I omega c, right. So, this is the expression we get for the amplitude of the complex exponential response, right. Now, this can be expressed in the magnitude and phase form like this. We can also write this as the magnitude of this is f naught upon square root of k minus m omega square plus omega c whole square into e to the power minus I psi, correct. So, here we have separated the magnitude and the phase part, okay, and what is psi here? This 10 psi, or maybe we can directly write psi. So, what is psi here? Psi is equal to basically 10 inverse omega c upon k minus m omega square, and psi is basically the phase lag. This is actually the phase lag, which shows the angle by which the particular part of the response lags the applied force. We can also further divide this, the numerator and denominator, by k, and make use of the properties that omega n is equal to under root k by m and zeta is equal to c upon cc, right. So, if you make use of omega n and zeta here, so we can write this expression for xpo bar also in this form. So, we can write this as x static upon under root of 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square, okay, multiplied by e to the power minus I psi, right, and the phase lag psi can also be written in terms of omega n and zeta as 2 zeta omega upon omega n divided by 1 minus omega upon omega n whole square, okay. So, in this way we obtain basically the magnitude and phase of the amplitude of the particular part of the response. Therefore, the complex response is given by xp bar t is equal to xpo bar e to the power I omega t, isn't it? And then we can find the actual response xp t as real part of xp bar t, isn't it? So, if you substitute now expression for xpo bar here, we basically obtained the real part of the response as x static upon under root of 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square, okay, and then e to the power I omega t into e to the power minus I psi will become e to the power I omega t minus psi, and then the real part of that would be cos omega t minus psi, isn't it? That is what we get. So, in this way you can see we obtained a particular part of the response to the actual force F naught cos omega t. So, let us go to next page. So, now we can write the total response, because the complementary part of the response already we have found in the previous part where we did the free vibration analysis. So, the total solution x of t, right. So, this is the total response or solution, and this is equal to xc plus xp, right. So, now let us assume the system to be underdamped, and then for the case of underdamped system we have obtained the complementary part as a e to the power minus zeta omega n t into cos omega d t minus phi, okay, this we got. And then we have the particular part which is x static upon under root of 1 minus omega upon omega n square whole square plus 2 zeta omega upon omega n whole square, right, into cos omega t minus psi, correct. So, that becomes basically the total response. Also note that here the a and phi, they are arbitrary constants. Here a and phi are arbitrary constants, and they can be obtained by applying initial conditions on the total response x. So, here we see that this part, the frequency of this part is, the frequency is omega t, isn't it, and it has a phase of phi, and then it is its amplitude it decays with time, correct. So, e to the power minus zeta omega n t, value of e to the power minus zeta omega n t reduces with time, and therefore the amplitude of this part reduces with time, and that is why this part is called transient part, because it basically reduces with time and then disappears after some time. So, therefore this is called transient part of the response. And now if you look at this part, the second part which is particular part, though the frequency of this part is omega, okay, while the frequency of the transient part was the damped natural frequency omega d, which is under root of 1 minus zeta square into omega n, right. So, that was a system property that depended on the system parameters, but the frequency of this particular part is omega, which is the frequency of excitation force which is acting, okay. And then the amplitude of this part is constant, okay. We can see the amplitude x static upon this term in the denominator, this is constant for a given omega. So, it means that this part will basically stay as long as the force is acting, okay. So, therefore, this part is going to stay. So, what happens as time progresses, the transient part would gradually decay and will become very negligible after initial time, and then only the particular part would be left, right. And therefore, in the steady state the total solution will be basically consisting of the particular part, and that is why the particular part is also called steady state part of the response. It is also called steady state response, because this is the part of the response that is going to be left under the steady state. Let us try to sketch the transient and steady state part in the total response. So, the transient part of the response is basically decaying in nature, right. So, it is going to basically decay like this, okay, and then we have the steady state part. The steady state part of the response is going to basically vary with frequency omega, and the amplitude of this part will remain constant like this, okay. So, this is x c as a function of time this is xp as a function of time. Let us sketch total response here like this. So, here we are going to sketch x as a function of time. So, okay. So, what we see in the initial part, there is presence of transient which is visible, but then after that the only the particular part is left, which is the steady state. Okay. So, we see that the particular part of the response, so the steady state part of the response, it depends on two factors. One is what is the frequency of excitation omega, and what is the damping factor. Okay. So, let us look at the steady state response. Right. It depends on the frequency of excitation omega and damping factor zeta, isn't it? So, if we try to show the variation of the steady state amplitude as a function of frequency for a given system with some damping factor zeta, then this will be essentially like this. So, here we are showing the amplitude xpo, right, and this would basically look something like this. Okay. So, this is basically the resonant frequency here, isn't it? So, we see that when omega is much less than omega n, then this response is basically equal to, amplitude of the response is equal to x static, right, and somewhere when the frequency is close to resonance and around resonance, the response is very high, and when omega is very large as compared to omega n, the response becomes negligible, right. So, it would be interesting to understand the dynamic equilibrium of different forces in a viscously damped system. So, let us try to look at dynamic equilibrium of forces. Okay. So, let us show on a complex plane the complex exponential forces. So, here we are assuming that the force is complex exponential of type f naught e to the power I omega t. So, the response x, the velocity x dot and acceleration x double dot, they also will be corresponding complex quantities, and these complex quantities then we can represent in the complex plane as rotating vectors. But the actual force and the actual displacement, velocity and acceleration will be the real parts of these complex vectors. So, taking the real part on the real axis basically will tell us the actual values of the force, displacement, velocity and acceleration. Therefore, we have, let us say this is the force vector, this is f bar, right, and then we have the the displacement vector is like this here, this is x bar, right, and it has a phase lag of basically psi. Okay. So, displacement lags the force by phase angle psi. Then we have the velocity, which basically leads the displacement by 90 degree, and then we have the acceleration vector, which basically leads the velocity by 90 degree, like this. So, this is how the force and various kinematic quantities are related. Let us now try to sketch the forces. So, we make another vector diagram here like this, and here again we are going to now show the force first. This is the force, right, which is F bar, okay, and now we are going to show the force due to elasticity, right, and that force would be basically this. So, here also we are assuming that the omega is much less than omega n, okay. So, all these diagrams we are making for the case when omega is much less than omega n. So, this would be basically the elastic force, force due to stiffness. Then we have the inertia force, which will be basically this, right, this will be m x bar double dot, and then we have the force due to damping, which will be this opposite to the velocity, which is c x bar dot, isn't it? So these are how different forces are placed, and now we can make a vector polygon of these forces as they are in equilibrium. So we have this force F bar, okay, then we have this force due to elasticity, which is this, which is k x bar, okay, and then we have the force due to damping, which is c x bar dot, and then we have the force due to inertia. M x bar double dot. So what we see here, that the one component of the force basically balances the damping force, and other component along with the inertia force balances the stiffness force. So this is how the dynamic equilibrium basically is achieved. Now let us see what is this equilibrium at when omega is equal to omega n. Omega is equal to omega n, right, when the resonance occurs, then what kind of equilibrium is there. So let us make that diagram. So here we have this the force, this is F bar, right. So the velocity will be in phase with the force. So the velocity vector is somewhere here, x bar dot, right, and then the displacement vector would be somewhere here, x bar, and then we have the acceleration vector, which is x bar dot, correct. And if we now make the force diagram, then this is the force F bar, okay, and now the damping force would be opposite to the velocity. So this is the damping force, this is x bar dot, right, and then we have the force due to elasticity, which is k x bar, right, and then we have the force due to inertia, that is inertia force m x bar double dot, correct. And now if you make the vector polygon of these forces, then that polygon would be something like this, that you have this the force vector, and then you have the force due to elasticity, which is k x bar, okay, then you have the force due to damping, which is c x bar dot, and then you have the force due to inertia, which is m x bar double dot, correct. So we see that at omega to omega n, inertia force and stiffness force balances each other, and the damping force alone basically balances the external force, and that is why the response is very high at resonance, okay. So only the damping force or the damping in the system basically controls the response at resonance, and because system is vibrating at natural frequency, it is expected that the spring force or the stiffness force will basically balance the inertia force, because that basically defines the equilibrium at the vibration at natural frequency, right. So let us finally look at what is frequency response function, FRF. So earlier we defined FRF alpha omega, right, as ratio of the steady state part of the response, okay. So in this case that response is x bar PO, right, divided by F naught, okay, and x bar PO we obtained as F naught upon k minus m omega square I omega c, okay, and F naught divided by F naught. So therefore what we get the expression 1 upon k minus m omega square I omega c, correct. So this is the expression we get for the frequency response function, and if we divide it by say m in the numerator and denominator, we can also write this expression in this form, omega n square minus omega square plus I 2 zeta omega omega n. So, we can also write this in this form. Okay. So, you can see that the FRF is now complex, it has both magnitude and phase. So, in this way we come to the end of this lecture, and in this lecture we basically discussed the free and forced vibration of single degree of freedom system with viscous damping. Now, we stop here. Thank you.